Hi, 8 Purple. Welcome back to another video lecture. Today we're going to talk about the reasons for seasons. But first, I want you guys to listen to the sound of pretzels. Mmm, that's good. Try another. Wow, that's pretty good. All right, let's get started. All right, so for our do now, I've got 5 questions up here. These are things that I think that everyone should know before we even begin a discussion about how seasons occur. So first things first, you should definitely know the difference between up and north. North is a direction on the globe, and it actually curves. It follows the Earth's surface, right? And it meets at the very North Pole. Up goes into space. Up is perpendicular to the ground. So those are two totally different directions. The reason why someone might confuse the two is because sometimes when you're looking at a two-dimensional map of the Earth, north is up on the map, but it really isn't. Try not to confuse north and up. Which compass direction does the sun move across the sky? Well, the sun always rises in the east and sets in the west, and it goes in the northern hemisphere. We see it move across the southern half of our sky. It's never really in the northern half of our sky too much. When viewed from above, which way does the Earth turn? It would spin counterclockwise. When viewed from above, which way does the Earth go around the sun? It too would go counterclockwise. So make sure you have those directions somewhat memorized. What is important about noon in regards to the sun's position? Well, noon marks the highest point of the sun's path that particular day. And there is a maximum for each day, and there's a maximum for each month, and there's a maximum for each year. So we'll get into those kind of important periods, I guess, those important dates or times later on in this chapter. All right, let's get started. So, why does Earth experience seasons? Um, so, first, a couple of terms that we should definitely know about. The first one is going to be revolution. This is when one celestial body orbits another. It's like kind of it's the actual path that it takes around the sun. This results in seasonal patterns, and then rotation is when one body spins around its own axis. So this is the Earth rotating right here. This does not impact seasons whatsoever, rotation, at least for our planet. It would result, this does result in daily patterns, though, but we'll talk more about daily patterns on another class. All right, so our first thing that's very, very important to do is to clear up one major misconception when it comes to seasons, and that is the distance to the sun. So these are terms that we learned last week, perihelion and aphelion. The perihelion is a point of an object's orbit when it's closest to the sun, and because all of our planets in our solar system follow ellipses, there's always a perihelion for each one, as well as an aphelion, which is the farthest point from the sun. So it turns out that our perihelion, our closest point is in January, where we're 147 million kilometers, and about 6 months later, we reach our aphelion during July. So we're actually farther from the sun in summertime than we are in wintertime when we're closer to the sun. So right there, that should automatically dispel the myth that how close we are to the sun is what determines seasons. However, here are the results from the exit ticket on Friday. This, which is basically asking that question. Earth's perihelion and its aphelion is its perihelion is in January, its aphelion is in July. Does the closeness of Earth and Sun determine when we experience seasons? 40% of you said it does. So I want to make sure that if you're someone who selected that yes on this question, that you're going to pay extra attention today because it does not. It has nothing to do with our seasons that we experience on Earth. So let's address why it does. All right, so let's say we have a little thought experiment here. We've got two ice cubes. One has a sun or some kind of heat source. Maybe maybe it's a sun, maybe it's a heat lamp, whatever. And it's directly above the ice cube. And then later on, we have a different scenario, different ice cube of the same size, and that sun, that heat source, is coming at an angle. Which would melt the ice faster? And the answer is scenario one. And this is why. So when energy hits something dead on, its energy is totally absorbed by that. When energy comes at something at an angle, it's going to bounce off of it, and its energy is spread out. So think of skipping rocks across a pond. If you took a rock and you just held it over water and dropped it, it's falling down at a 90 degree angle to the surface of that water. And because it's coming at 90 degrees perpendicular, it's going to be completely absorbed by that water. All that energy is going to turn into a splash, and then the water will absorb the rock. In this case, the rock is the energy. Um, Whereas if you take that same rock and you throw it at a very shallow angle across the water, it has a potential to skip off, and that energy is reflected in a sense. So with a lake, that lake keeps going on and on and on and on. But on an Earth's surface, sometimes that surface is, or always, that surface is curved, and the solar energy can bounce off of it and just go right back into space. So that's one reason that the angle is important. The other is the concentration. So if we kind of, I mean, this is, it takes some stretch of the imagination here, but if we think of each one of these lines as a unit of energy, and the sun is releasing 4 units of energy, all of that energy is concentrated between this point and this point, right here and here and here. So that's a very small section of energy being hitting it right there. Whereas if you take those same 4 units of energy, look at how much energy, how much more surface area that energy is spread out over. So that energy isn't going to heat up this section of Earth quite as intensely as it would over here. So those are 2 reasons why angles make a difference. It's concentration and reflection. Okay, so that angle actually has a name. It's called the angle of incidence. This is the angle at which a ray of sunlight strikes a planet. This is in blue, so make sure you write that down somewhere. The strongest sun is when the angle approaches 90 degrees, just like when you drop a rock into water. The weakest sun is when the angle approaches 0. And if you notice, there's something important about the orientation of our globe in these 2 scenarios. Here's summertime, June 21st, and here's wintertime, December 21st. This is the start of summer and the start of winter. If you'll notice, the angle of the Earth is the same in both pictures, and it's in both scenarios, it's tilted to the right. It's tilted towards the right over there. So that's gonna be a big factor in why we experience seasons. Okay, the big idea is this. Because the Earth is tilted and because that tilt is in a fixed position, just like we showed in this picture, right? The tilt is always going to the right. Here, the tilt is going to the right. So because we have a tilt and because that tilt is fixed, different latitudes on Earth will experience different angles of incidence of sunlight. So these pictures were taken on the same day. This one, it almost looks like a bad rendering of a video game because there's no shadows, but the sun is directly overhead, so it's not going to cast any shadows. There's no shadow to be cast. Whereas here, that sun is at a very, very shallow angle, and it's going to produce very, very long shadows. A lot of this energy is being spread out over a huge distance, and a lot of it is reflecting off of the atmosphere and going back into space. Whereas here, all that energy is concentrated directly onto every square inch that the energy is hitting. All right, so looking at this again, here we have June 21st. This is one day, and what we're going to do is we're going to take our little man here, and we're going to change his latitude and see how much angle, what the angle is of sunlight that they experience. So right here, this person is on the Arctic Circle, and they're experiencing about 60 degrees of sunlight. You can see here's 10, 20, 30, 40, 50, 60 degrees of sunlight. And for them to see the sun, they would have to look kind of upwards, right? So if their eyes typically go parallel to their arms, like that, look out parallel to your arms, they would have to look a little bit up to see that sun when it crossed over at noon. It would be about 60 degrees in the sky. Here we have someone on the Tropic of Cancer. Here, this person would need to look directly over the tops of their heads in order to see the sun. So this is indicating that that sun is really hitting this latitude with extreme prejudice. Lots and lots of energy and intensity is hitting right there. This person at the equator is getting pretty high sunshine as well. Not quite as intense as the Tropic of Cancer, but more so than the Arctic Circle. They're getting about 70-degree sunshine right here, which is a good amount. Down here, the southern latitude, they're experiencing about 40 degrees of sunlight at this time of year. This is summertime. And then here at the Arctic Circle, this person is going to be getting 0 degrees of sunlight. So the sun is coming at this point, and you can see this line right here. This is kind of separating the side that's being hit by sunlight and the nighttime. They're right on that line, which means that the sun is just at the horizon, hitting the Earth at such a shallow angle so as not to really do any kind of heating up. One more thing I should mention is this concept of precession. Precession describes how the tilt of a planet wobbles. And our planet does actually wobble. It just takes about 26,000 years to do so. So we don't really notice that difference. And in about 12,000 years, we'll no longer be pointing to the North Star as we are right now. We'll have spun around, or precessed, I guess is the right term. We will have precessed and we'll point at the star called Vega. Now, because this is such a slow process, we're going to ignore the concept of precession for explaining seasons because it has no impact on a human's experience throughout their lifetime. All right, so let's talk about the axial tilt of the planet. That's really important. Our planet is tilted at about 23.5 degrees. And this tilt is probably, although we don't know for sure, it's probably a result of some major impacts early in our Earth's history, perhaps when the moon impacted Earth. It kind of it pushed it off of its vertical standing and made it tilt about 23.5 degrees. And right now, this dotted line here, that is pointing directly at a star that we call Polaris. That's our North Star. And here it is. So if we were looking north, which is what our vantage point is right now, if we were to open the shutter on a camera and have a long exposure, we would see stars looking like they're spinning around. Um, and they'd all be circling the center point here, the North Star. And that's kind of how you would orient yourself. This is going to be a fixed object in the sky, this North Star. That's not going to move whatsoever. It's always there, and the stars are kind of spinning around it because that's what the globe is doing. But the stars aren't really spinning, are they? What's really happening, this is kind of cool. So here's Polaris again, and we're looking north. What's really happening is the Earth is rotating, and the stars, those are kind of fixed and we're spinning around, and this is really what's happening. So here, instead of the stars making that really neat kind of pattern, the Earth is orbiting, or is rotating around this axis. You can think of the axis right here coming out of Polaris, coming right through the screen and going through the center of the planet Earth, just like this, right? It'd be coming down just like that through the Earth, and we're standing somewhere here looking at Polaris, and the stars spinning around it. Okay, the other thing I want to talk about is revolution. This is when one body orbits another. A completed revolution is equal to one period. If you happen to be on Earth, that's 1 year. But as we saw last week, all of the planets have different periods, and therefore they spend more or less time going around the sun in their revolution. The ecliptic is another term. The ecliptic is the path that the Earth follows during its revolution. It's kind of like the ecliptical plane. You can think of this as like a very thin frisbee. Think of it like that, like a plane. And that plane is called the ecliptic. The Earth goes around the sun in a counterclockwise motion. And while it's revolving around the sun, it's also rotating about its axis in a counterclockwise motion as well, when viewed from above. All right. This is where the sun would occur at noon at different times of the year. So like we said earlier in the do now, we should all recognize that our sun, oops, let me just kind of grab one of these guys. There we go. Our sun always starts in the west. We can't see west here. We can see southeast. Starts in the west, and it comes up this way, and then it sets in the east. I'm sorry, I have that totally backwards. The sun rises in the east, and then it sets in the west. Every single time, every day. But really, again, it's not that the sun is moving, it's the earth is spinning, but it gives the illusion the sun is moving across the sky. In the wintertime, that sun is going to take a very low path. It's not going to be very high, and it's going to be kind of southeast, and then south, directly south at noon, and then southwest. And then as we get into summer, as we get closer and closer and closer to summer, to June, that sun gets high, that noontime sun gets higher and higher and higher. Until you get to June 21st, and then it starts coming back down again each passing day. One thing that's important to note is that at noontime, typically around noon, it's not exactly because of daylight savings and some other things about time zones, but around noon, that's when the sun is going to be directly south. So that's one way to orient yourself. If you know it's noon and you look at the sun, that should be a southern heading for you, at least for people in the northern hemisphere. This would be this opposite perspective. So if this was us on Earth, and if we had a kind of a big fast motion, you would see the sun going up and down throughout the year. But if you change your perspective to that of the sun, you would see the Earth wobbling like this throughout the year. It's very fast. It'd be like a summer, winter, summer, winter, summer, winter, summer, winter, something like that. But yeah, it's kind of an interesting animation of what the Earth would look like from the sun's perspective. Okay, so let's close things up with exactly why we have seasons here on Earth. There are three main things. The Earth is tilted on its axis at 23.5 degrees. That tilt is always oriented towards the same direction, which is Polaris, and the Earth revolves around the sun. These three things cause changes in the angle of sunlight hitting Earth's surface at different latitudes throughout the year. So that is why we have seasons. Okay, thank you so much for watching, and here's some more pretzels. Mm, that's good.